maybe plot from minus 10 to 10. That's what it looks like. This is a real surface, not one that is drawn by me. It's cool. This is what you do with a 3D printer, you'd make this.
Like a hologram. Wouldn't that be cool if we had some like hologram here in the ground? I always thought like for like Calc 3 that would be the perfect thing.
Yeah, where people could actually go and see
right?
it. Like
let's modify the equation, which pops up and
right around the kid that's sleeping.
Right? Like a Rubik's Cube that would be here and do that.
Yeah.
It's
Just saying.
some engineers in here.
I mean, things have progressed so fast, because when I was taking Calc 3, all I had was my professor's phony pictures in his head. Like,
Right.
I don't know what's in your head, dude. And now you can draw them on Maple, and I'm sure that technology exists where you can actually see it pop up in the center of the room.
Well, they have something there where it was like NBC or one of the channels, maybe Fox or something, projecting a hologram.
They did that with that,
The election.
Always for
Yeah, something like that. Yeah. So the technology's there.
It's just being used for 2 blocks.
I mean, that's the joke. I mean, that's for the magician to take and make the hologram.
Too bad.
It can be reduced to a simpler problem, and the exercise is left for the readers.
All right. Very sharp. Very important.
I feel bad enough I left my purple one.
Oh, I love the purple ones. They're the best. Maybe these are staples. I like these. They're pretty like bold.
Yeah.
I think I put pre-calc solutions inside your PDEs, or maybe the other way around, which is probably worse, but I couldn't get it back out. So I tried to delete it out of there. It might be other way around. It might be the PDE solution in the pre-calc section.
I hope so.
They would look at it and be like,
Don't worry, I think they might be looking at the pre-calc like that as it is.
I gotta say one thing, after enough years of doing this, my board work is way better than my real handwriting.
yeah, right. Well, that's good for me.
Yeah.
Let's see my handwriting.
So I'm starting to really enjoy what we're getting into, because we're actually getting into the equations, and it's starting to connect up, and I feel like the book is going along a little better. There's less bouncing around, and I think we can move more slowly and kind of pick at these things. The first thing is that we need to start with the divergence theorem and Green's identities, which that comes at the end of Calculus 3. And it's not really clear when you're at the end of Calculus 3 why they're important, but really what they entail is they're partial integration, or integration by parts in multi-dimensions. So the intuition behind the divergence theorem is that you have a region, omega, that's what he's calling all the regions, and the boundary around the region. Now when he's talking about the region, he's talking about a surface, and then he's talking about the boundary of the surface, or a volume, and then he's talking about the surface, right? So doesn't have a boundary, but I drew it in 2 dimensions so you can actually see it and think of what it is. And by the way, this little symbol up here, so I'm not going to move. I actually listened to it and I saw my voice fading in and out. This little symbol here means boundary. So suppose inside that boundary I had some kind of vector field. That was my drawing of the vector field. What the flux represents is the total amount that's whatever you're drawing with that vector field. It's the total amount that's flowing through that surface at the edge. So what we want to compute in the divergence theorem, as part of the divergence theorem, is the flux across the boundary. And just like anything else in calculus, you take a little piece first, and you analyze how you do this with a little piece. So the first thing you want to look at is the outward normal vector, which is standard in looking at these problems. And it turns out that the formula for the flux across that little piece is the vector field dot the normal vector times the length of that little piece. That's that delta r. So if that's the little piece, then you add them all up all the way across so you get an integral, and you're really integrating over the boundary and taking this f dot n dr now instead of delta r. What the divergence theorem tells you is that the flux across the boundary is the same thing as taking the double integral, because I drew it in 2 dimensions here, of the divergence of f dx dy. And the way your book has it is instead of dx dy, they're thinking of it in 3 dimensions, so it's ds, because they're integrating over a surface. So here I'm giving you the 3D version that he has in the book. The total divergence of a vector field in a solid region V. V he has for volume, indicating that he has some kind of solid region. It's the total flow across the boundary of the surface. So you have to take the picture I drew in 2 dimensions with omega being the region and the boundary, and think of instead like maybe a paraboloid, that's the volume that you're looking at, and then that surface of the volume would be the outer part of the volume. So everything scales up 1 dimension. And that's what it looks like in this is what you have in your book. So the left-hand side, which used to be a single integral, is now a double integral, and the right side is a triple integral. And this may be how you saw it, if you saw it at all, or if you remember it from Calc 3. It's kind of hard because it's one of these things that's discussed at the end of the semester, and everything kind of goes down the tubes at the end of the semester. So in a way, this is integration by parts in multi-dimensions. Just to show you that, you can revise integration by parts and look at it as information across the boundary, that's the fundamental theorem of calc, where you're just evaluating from A to B, is equal to information about the area. So you're taking 1 dimension and relating to something in 2 dimensions. And in fact, Michael Loss used to always call our divergence theorem applications partial integration. That's what it is. So in your book, this is what's missing. It's like you want to actually do a calculation by hand where you can see what it is. So let's just take something easy like the surface of a box. So I made a box from 0 to 1 on the x-axis, and I'm not Bogdanita. I couldn't draw it as well as he would, but that's my attempt at a box. When I heard that there was a computer that would draw these things for me, I was in bliss. And I made up a vector field, and I didn't really make this up. I got this somewhere, probably off of YouTube. But what the point of this vector field is, it's not a pretty looking vector field. It's scary looking. And this is the whole point of using the divergence theorem. You have something scary, but when you recouch it in the terms of the divergence theorem, it becomes easy.
What C raised? Is that
77, yeah.
It doesn't really, we're only getting to according to x.
Right.
Yeah, no.
So let's say you have that scary vector field, and you wanted to calculate the flux across the boundary. Well, let's look at that ugly thing again. That's what we have. The divergence of that ugly thing is not bad, as you noticed. If you take the derivative with respect to x, and then add the derivative with respect to y of the second term, and add the derivative with respect to y of the third term, it really doesn't look so bad at all. So it's actually nice. But what the divergence theorem tells you is that the flux across the boundary is equal to the divergence of f dv, and you're integrating over the box. How to translate that integral, because in your book what they'll have is just 1 integral symbol. They won't have a triple integral, but I'm telling you it's a triple integral. That's what you're calculating. So in your book they'll have just 1 integral symbol with v underneath it. What that means is it's a triple integral, and what the v means, you're actually calculating the limits of integration across that integral, across that volume. But because I have a box, the limits of integration turn out to be just the endpoints of the box. And the divergence, as we just calculated, is really nice. So just to walk you through these calculations, maybe I'll actually assign you a couple of these just to remind you, because I remember going through this and I didn't have a good feel for my Calc 3. And going through Zachmann-Glow's book, he just has this single integral symbol with the v underneath it. I couldn't picture in my head that I was actually calculating a triple integral. So and yeah, after a while, after you see it and after you get roughed up a bit, you realize that that's what's going on. But maybe for us, it might be nice to get our hands dirty first and calculate some of these, just simple ones, so you get the feel of it. So I just did the triple integral. How it works is you start first on the inner integral, just to remind you. So I just did a straightforward, started with dx, and then I was lazy and I just did all the calculations on Maple, so I went and just integrated. It's just a polynomial, and then evaluated. So I skipped a step here. So what I did is I took this 3 plus 2y plus x, integrated it with respect to x, so I get 3x plus 2yx plus x squared over 2. And then I evaluated that mess from 0 to 1. And this is the result. You'll get only a function of y because the x's will drop out because you plugged in numbers for them. Then I took this function of y right here and integrated that with respect to y because that's the next. And if you recall, Fubini's theorem allows you to rotate the integrations around. So I could have done this probably in the simplest way possible. Probably z would have been the easiest, right? Because there's no function of z. But it didn't matter to me. I was lazy and ran it through Maple. And so you integrate this second integrand over here with respect to y and do the same thing. Apply fundamental theorem of calculus. All the y's drop out and you're left with 39 halves. And then you integrate that with respect to z and use the fundamental theorem of calculus here and you end up with 39. So that's a flux across the boundary of that box. So it's actually a very powerful theorem. And what it states in words is that the integral over the omega of the divergence of the vector field is equal to the integral of the boundary over the boundary of the region. So it's pretty powerful. And really amazing if you think about it. With knowledge of only the boundary, information at the boundary, you can tell something about the volume. Knowledge of only the volume, you can tell something about the flux. That's pretty amazing. So what are Green's identities? I'm not going to prove both of them. I'm just going to go through one of them. They're just relationships that you can derive starting with the divergence theorem. So recall that the gradient is this guy over here. Then the divergence is the gradient squared, which we know. But I'm going to take the gradient, I'm going to take the divergence of the gradient, which turns out to be second derivatives. That operator is called Laplace's operator, and it's actually, the way I've usually seen it is as a right side up triangle. I actually had a student who, I trained him, he knew all his theorems, he knew Lebesgue's integration theorem, he knew it all. And he went to do his presentation, and he starts out saying, upside down triangle U is equal to, I'm sitting in the back, this is my first research student, and I'm going, oh no, oh no. Right side up triangle. So you can actually calculate these by hand and prove them, that these relationships hold right here. So you can prove that one. It's not that hard to prove. You just go through, you calculate U, Laplacian W, and you show that it's the same thing as the right-hand stuff on the, so you just do the calculation forward. So that one's algebra mostly, with a little bit of calculus tossed in. So realize that this is a triple integral if they're doing it over a volume, a three-dimensional volume. I'm going to start with this left side. Well, it's multi-dimension, so you have to prove it. You have to prove it. That's what it is. I told you this is related to integration by parts. So prove that identity, that blue identity up at the top. We're going to calculate that black integral on the left that I have under a bracket that says a triple integral. What you do is you take that black triple integral and you drop in the identity above and split up the integrals. And then what you get below is, let me back it up. So what is this piece over here at the bottom where I have a question mark? It turns out that that piece is really the gradient dot the vector field dv, which is equal to u. It's gradient w dot the outward normal ds. That's the flux, right? So you're applying the divergence theorem. And so you get this identity up here, and it's called the first Green's identity. So you're really just taking divergence theorem and using it to come up with some other relationships. And these other relationships are going to be used to look at the PDE. And just go ahead and read the derivation of the second Green's identity. It's the same thing. You're just substituting some formula and applying the divergence theorem, and you'll get another identity or another piece of information you can use.